My name is Bryce Carlton and my project covers optimization of lift on an airfoil. The problem I addressed was using genetic algorithms and simulated annealing to optimize the lift generated by an airfoil as determined by a vortex panel method. The design variables were the y coordinates of the endpoints of each panel, and constraints for airfoil thickness at various chord locations were introduced. The results varied greatly between genetic algorithm and simulated annealing methods, but overall the results weren't very smooth. This simulated control surface deflections of an airfoil. Lift optimization is important for overall aircraft design, especially when thickness constraints may be driven by other design decisions, such as equipment installation or other structural considerations. The goal is always to find the optimal airfoil design for a given application. This leads to a typical problem of maximizing an objective function subject to various geometric constraints. Airfoil design has been a major feature of engineering since the early 20th century. NACA developed many standardized airfoils in the 20s and 30s, which were thoroughly tested to determine their properties. Now, CFD is primarily used as an optimization tool, but can quickly become complicated. Vortex panel methods are an intermediate step between test and CFD analysis. For later comparison, note that the NACA 4412 airfoil in the lower right has a coefficient of lift of 0.4 at zero angle of attack. Vortex panel methods make the steady, inviscid, incompressible, and irrotational flow assumptions to simplify the Navier-Stokes equations, and typically provide reasonable accuracy while avoiding complexity of full CFD models. In this case, I used a combined source vortex panel method, which uses sources and sinks to define the shape of an object, and a vortex term to define circulation, which leads to lift. This requires n+1 equations with n+1 unknowns be solved for an object constructed of n panels. I created a MATLAB function, VPM, which solves the source vortex problem for an airfoil constructed of 50 panels. Due to differentiation of the panel method equations being non-trivial, MATLAB's genetic algorithm and simulated annealing functions were used for optimization. A continuous design space and boundary constraints were included. Other constraints were not used due to limitations of the simulated annealing function. The optimization script itself was fairly simple once VPM was created. Boundaries were set to control airfoil thickness, and the optimization functions were run using VPM as the objective function. Results were then plotted. Here are results using only maximum and minimum thickness constraints. Notice that the airfoil is very thin with spikes near the front or back to increase camber, which simulate flaps or slats. This is a second run using GA with the same constraints. Note that a different result is obtained, and another feature increasing curvature has appeared near the center. This is likely due to the technique used finding different local optima for the given constraints. This result occurred when a larger minimum thickness constraint was added for the first third of the airfoil, and is probably the most realistic looking result. Note the camber of the airfoil and the control surface-like object at the front. This could simulate something such as a Kruger flap. The results of simulated annealing were much less realistic in both shape and magnitude of lift coefficient. Note the lift coefficient is many orders of magnitude higher than the NACA 4412. Identical constraints were used between this and GA, but the output is much more random. And here is a second result using simulated annealing with similar features. With minimum constraint usage, fairly realistic representations of airfoils with high lift devices, such as flaps, were obtained. Due to the heuristic techniques used, different results were obtained from the same inputs, and overall, GA seemed to provide more realistic results than simulated annealing. Further investigation of the topic could prove useful. Primarily, refinement of the boundary constraints could improve the results, and existing airfoils could be optimized by approximating their overall shape using constraints or initial guesses. While the vortex panel method provides a quick approximation of lift, optimization using CFD would provide more accurate results and is a logical next step for further application.